Hello friends, so welcome to our first lecture on Introduction to Detection Theory. So in this particular lecture, I will introduce the detection theory, and then we will also discuss the binary hypothesis testing, and then we will talk about the four kinds of the four parameters in detection theory for binary hypothesis testing. So let us start. So let's first understand what is detection theory. So detection theory could be applied into many different areas. For example, take an example of a radar. Okay, so let's take an example of a radar. So in radar, so you have a radar here, and what it does, it sends out a signal. There may be an airplane somewhere. What the radar has to do is it has to detect whether a plane is there or not. To detect whether a plane is present or not. Okay, so it is a detection problem. You can see a detection problem here. Detect a plane, whether a plane is there or not. So depending on the signal it transmitted, then the signal will be reflected back. Okay, and then this reflected signal will be received at this radar, and from that received signal it has to detect whether a plane is present or not. So this problem also decomposes into finding whether a noise was detected or a signal plus noise was detected. Okay, so when the question is a option problem, whether option A is correct or B is correct, then it is a detection problem that we discussed in the class. So this is option A and this is option B. Okay, so if you are looking at option problems, then it is a detection problem. Okay, one of the option is correct. You have to figure out which option is correct. Okay, the second example that we discussed was about the bit being transmitted in a communication system. Okay, so as you all know, in a digital communication you want to transmit either 0 bit or a 1 bit. So 0 bit is transmitted by, let's say, a sinusoid with, say, cos 2 pi f c t. A 1 is transmitted with, let's say, cos 2 pi f c t plus some phase difference, let's say a 180-degree phase difference you want to transmit. So what will happen is that from the transmitter, so at the transmitter side, you will transmit these bits in the form of these sinusoidal waves. So these sinusoidal waves will travel, and at the receiver you will receive these waves, and you have to detect whether you detected this waveform or this waveform. So again it is a option A or option B was detected. So this is again a detection problem. Okay, the third example I'm going to take from, let's say, image processing example. So in an image processing example, suppose you want to figure out whether which digit is there in the image. Okay, so I am writing a 0 here, I am writing a 1 here. So you have to detect from taking an image of this whether I am writing a 0 here or a 1 here, and so on. So there could be multiple options. Okay, not just two but multiple options may be there. Okay, so 0 to 9 there are 10 digits, so there are 10 options in this. Okay, so this is again a detection problem where you have multiple options and one of the option is correct. Okay, so this is in general a detection problem. So in general a detection problem is similar to a multiple choice question problem or an option problem. Okay, so it is different from estimation problem where you try to estimate some particular real number. Here we are trying to detect means one of the options is correct, whether a signal is there or not, or whether the image I have shown you has a 0 or a 1 or a 2 and so on. Okay, so if you have two options, if we have two options, then it is called as a binary hypothesis testing problem. Okay, and when we have more than two options, then we call it to be a multiple hypothesis testing problem. Okay, so so this is pretty clear. Now there is one more thing. See, there could be, so what is the input to the signal, input to the system? So this is, let's say, your detector, and detector will give option A is correct or B is correct or C is correct and so on. So the number of options are there. So one of these are correct. Detector will give you this. It will take input some signal. Okay. Now this signal could be a continuous time signal. Okay. Or it could be a discrete time signal. Okay. Or a discrete time signal. Okay, so we what we are going to do, because of the advent of the digital processors, we are mostly working on digital signals or discrete time signals. So we will look at these signals by and large. Okay, so we will have signals which are available at different time instance, not the continuous domain but in the different time instance. Okay, so we will have signals at discrete times, and from them we will use some algorithms to detect which option is correct. Okay, so this is what we are going to do in the detection theory. Okay, now let me take a very simple example of a classical binary detector. Okay, so let me take a small example of a binary hypothesis testing. Okay, so let's take this as example and understand more better what do we mean by detection theory. Okay, so I'm going to take the example from a radar system. I'm again going to take the example of a radar system. So these detection and estimation theory were primarily built for radar systems, but then as the time progressed and number of other applications came up, these theories were applied to many different application areas. Okay, so the terminologies that have been used in detection theory have been borrowed from the radar systems. Okay, so let me take this example of a radar system. Again, I'm drawing this graph. So this is my radar. What a radar does is it transmits some waveforms. Okay, what will this waveform do? It will go in this space or wherever you want to transmit, and if there is an object there, let's say an airplane is there, what this wave will do, it will go and then reflect back. Okay, so this will be reflected back, and when it is reflected back, it is again received at the radar. So depending on what you have received at the radar, you will decide whether the aircraft was present or not. Aircraft was present or not. Okay, so I have one example. So two options. aircraft absent, and the second option is aircraft present. Now, when will the aircraft be absent? When there is no signal being reflected by the aircraft. Okay, so that means what you are receiving here is you receive noise only. Okay, and when will the aircraft be present? When there is a signal being reflected back from the aircraft. So what you are going to receive is you will receive signal, maybe a distorted version of the signal, plus noise is received. Okay, so these are the two options that we want to test. So we will have some signal that is received at the radar cross section, and we have to judge whether we received only the noise or we received signal plus noise. So more mathematically, let me write down mathematically. So suppose x at time 0 is the signal that I have signal received by radar at time 0. Okay, so now there are two options. X0 could be equal to W0. W0 is again the noise, our additive, sorry, the white Gaussian noise. We are taking, let's take this assumption, white Gaussian noise. So my received signal could be either noise, or it could be either a signal, let's say a signal which is of, let's say, amplitude A, constant amplitude A, plus noise. Okay, so this is my signal plus again my white Gaussian. All right, so this is my option 1, this is my option 2. All right, so in binary hypothesis testing, we also give names to these signals. So if there is noise only present, this we detect. So we also name it and say this is hypothesis 0. So let me write here, this is hypothesis 0, or also known as null hypothesis. This is also known as hypothesis 1, or it is also called as alternate hypothesis. Okay, so our job here is to figure out which one of these hypotheses is correct depending on the signal that we have received. So what I'm going to do is I will have this x0 to my detector. Okay, x0 will be the input to my detector, and the output is going to be either h0 is correct or h1 is correct. This is the job of my detector. Fine. Now let me draw. So I have also given the expressions when hypothesis 0 is correct and when hypothesis 1 is correct. So I can also draw the PDFs or write the PDF of these signals that I have received. So let me write down the PDF. So the PDF of x0, suppose if hypothesis 0 is correct, will be what? Will be the PDF of W0, and the PDF of W0, as we all know, white Gaussian noise. Let me take this to be a normal distribution with mean 0 and variance sigma square. So I can write this PDF as 1 over under root 2 pi sigma square e power minus x0, okay, whole square divided by sigma 2 sigma square. Okay, so this is going to be yeah, it is x0 square. Okay, x0 or w0 is one and the same thing. Okay, I can also write the PDF of x0 given the hypothesis 1 is correct. Suppose there is an aircraft present, that means the signal is there. This is, I'm taking a DC component signal here. So this is the PDF of this. Okay. So this is equal to 1 over under root 2 pi sigma square e power minus. Okay. It is going to be x0 minus a whole square over 2 sigma. Alright, so these are the two probabilities that you are going to get for hypothesis 1 and for hypothesis 0. Alright, now there are many ways of making detection. So as we did in the classical estimation theory, in estimation theory we had two ways of doing things. So in estimation theory we had one which is called as the classical, the other one was the Bayesian. In the same case here also in detection we have two things, the classical one, so there are classical methods and then there are Bayesian methods. Okay, so in classical methods we do not know with what probability H0 or H1 occurs. So this is our prior. Okay, the prior is probability of occurrence of H0 or H1. Okay, this is the prior. So if this prior is not provided, then we use classical method, or if we do not use the prior, then we use the classical methods. If the prior is provided, that means the probability of occurrence of H0 or H1, then we use Bayes methods. Okay, so what we are going to do is we are going to look at some of the classical methods. In this, the primary one is called as the Neyman-Pearson theorem, which we will see in the subsequent lectures. In Bayesian method, something called as Bayes risk method is there, which we are going to look at in the subsequent lectures. Okay, fine. Now let me talk about more detail about the binary hypothesis testing. Let's go into more detail about the binary hypothesis testing. So I have written down the PDFs also of the binary hypothesis testing. So let me draw the graph also for these PDFs. So again, let me recall these two things. So I'm doing a binary hypothesis testing, and I have two hypotheses. Hypothesis 0 means x0 is only noise, and hypothesis 1 is x0 is signal, which is, let's say, some DC value and the noise. Okay, and I've also written the PDFs of x0 given h0, which is equal to 1 over under root 2 pi sigma square e power minus x0 whole square over 2 sigma square, and the probability of x0 given the h1 is equal to 1 over 2 pi sigma square e power minus x0 minus a whole square over 2 sigma. Now let me draw these two graphs, and then we will discuss a few more essential things. Okay, so let me draw the graph of this one. All right. So on the x-axis I'm drawing x of 0. On the y-axis I'm drawing the probability of x0. Now suppose if h0, the hypothesis 0 is correct. So I'm taking this case. If this is correct, then let me draw the graph. So the graph is going to be a Gaussian curve with mean 0. Okay. So this is a Gaussian curve with mean 0. So this one I am naming it to be probability of x0 given hypothesis 0 is correct. Now let me do the same thing with the hypothesis 1 also. This is what? This is again a Gaussian curve with mean A, variance is same as sigma square. So it will be something like this. So this is A, okay, and this I'm naming it to be probability of x0 given hypothesis h1 is correct. Now what is our job as a design engineer or as a communication engineer or as a detection engineer? Our job here is to take this x0 and we have to design a detector. We have to design a detector such that we tell which one of the hypotheses is correct, h0 or h1. So this is our job as a detection engineer. Okay. Now how I am going to do this is I am going to look at this value of x0 and place a threshold over it. Okay. So I can say that if x0 is greater than some value threshold, let's say gamma, then I'm going to decide that h1 hypothesis is correct. If it is less than gamma, then I'm going to decide that hypothesis 0 is correct. Okay, so let me draw this. Let me take the gamma here. So let's take this one as to be gamma. Okay, so if I get x naught which is greater than gamma, I decide h1 hypothesis to be correct. If it is less than gamma, I decide h0 hypothesis to be correct. Okay, now there could be 4 cases here. The 4 cases, I can highlight the 4 cases here in this way. So let me write it. 4 cases. So the first case is, so this is true scenario. This is detected. And this is, let me write it as terminology. Now what can happen is that in true scenario, let's say there was no plane. Okay, so there was no plane means h0 was true. Okay, so there was only noise present, there was no signal present. So what is going to happen is that x0, what you are going to get is according to this red curve. Okay, so what you are going to get is you are going to get x0 which will be only noise, and this will follow the PDF given by this red curve. Okay, so now given this x0, what is the probability that you detected h0? The probability of detecting h0 is the probability that you get your x0 to be less than gamma. Okay, so if you detected h0, what is the probability? Probability is, here the probability will be, so this is again a Gaussian curve, so you will integrate from minus infinity to gamma. The PDF of this curve is probability of x0 given h0. Okay, so this one I'm writing, this is given by this expression here. Okay, and then dx0. Okay, so if there was only noise present in the signal, there was only noise present, then your hypothesis 0 is correct, and you will detect h0 hypothesis when you get your x0 to be less than gamma. And what is that probability? That probability is given by this expression here. Okay, the other option could be your x0 is greater than gamma, and then in that case what you are going to get, you will detect it to be h1, and the probability of detecting this x0 to be greater than gamma, so this probability is going to be from gamma to plus infinity, probability of x0 given h0 dx0. Alright. So with this probability, what you are going to detect is you are going to detect the hypothesis 1 to be correct, though hypothesis 0 was true scenario. Okay. The same thing you can do with hypothesis 1 also. Suppose there was signal present, so hypothesis was truly correct. So what you are going to do is you are going to draw x0 from this particular PDF, the blue color PDF. Okay. So if you get x0 to be greater than gamma, then you detect your hypothesis 1 to be correct. So let me write here to be hypothesis 1 here, and the probability will be from gamma to infinity, probability of x0 given h1 was correct dx0. And similarly for the other case also, if the hypothesis 1 was correct but your signal x0 was less than gamma, okay, it lied in this range, then you detect your hypothesis 0 to be correct, and this is with probability minus infinity to gamma, probability of x0 given h1 dx0. Okay, so these are the 4 scenarios that can happen in this case. Okay, depending on the true scenario as well as depending on the true scenario you will get a PDF, and depending on what value you get from that PDF, you will detect but one of the hypotheses to be correct. Now these I should not write here terminology, but I should write the PDF. So this is PDF, or rather the probability. And obviously there are certain names to each of these events. So let me write here terminology. And so we all know if H1 is correct and we detected it correctly, then this is called as probability of detection. So this is called as probability of detection. If let's say H1 was correct but we detected H0, so this is called as misdetection. Misdetection. Or in other words, we also call it as a miss. Okay. Now there is another terminology here. If H0 was correct, means there was no aircraft, but we detected it to be an aircraft was there, then we call it to be a false alarm. Okay. And the fourth one is not given any name, but we call it to be specificity. Okay. And detection is also called as sensitivity. Okay. So these are the 4 cases that we have. All right. So each of these cases are given a particular term to it. There is also some terms given to it. This is also called as this false alarm is also called as type 1 error. And this misdetection is also called as type 2 error. Okay. So there are two such terms given to these things. Okay, so we will stop here, and in the next lecture we will discuss further on how to go about deciding this threshold gamma. So how to decide the threshold? So this we are going to discuss in the next class. Thank you very much.